Hello, everyone. Thank you for attending to our virtual workshop about the Dolomite Microfluidics today. So my name is Ching Nguyen. I'm a technical application specialist of the Dolomites in Asia Pacific regions. So today we would like to talk about the droplets and particles generation by using microfluidic technologies and its applications. So it will including the three sections. So the first section will be going with presentation. The second section will be going to the live demo sections, and the third section will be Q&A, question and answer. So before going to each sections, I would like to mute all the microphones from your side to make sure that there's no unwanted noise from your side, which can be affected to the other attendees and the workshop. So for any question, as you just feel free to ask me by using the chat box. So I will try to answer all the questions in the workshop time in the Q&A section. So if there's many questions or I cannot the answer in time, so I will answer later, give response later through the emails to all of you. Thank you. So let me start to sharing my screen to everyone to start section 1 with presentation. Sorry, so I need to check so everyone can hear me as well, or I just need to reduce my voice, just using the chat box to make sure that.
Very clear sound, Dr. Chin.
Sorry?
Okay. We can hear very clear, yes.
Okay. So let me start with presentation. Okay, so everyone can see my screen or presentation?
Yes, you can see.
Okay. So today's presentation will include the introduction and how does technology work, and the application with microparticles and nanoparticle, PLGAs, and liposomes, nanoparticles, and the other application. And finally, we will discuss about the system and scale. The first introduction, Dolomite is a part of BlackTree Group, and with the blog design and shared market leading products through the order. Our global leading brands, with including the Dolomite. So Dolomite provides microfluidic-based solution for a range of applications, including drug encapsulation, droplets manufacture, and particle generation. And second brand is Particle Work. So we provide precision engineers, nano and micro materials. And third brand is Dolomite Bio. We provide innovative product for high output single cell research. So we have more than 100 people globally with headquarters in Royston, United Kingdom. And we have three offices in the US, Japan, and Hanoi, Vietnam. And we have distributors in more than 25 countries in the world. The Dolomite Particle Engineering team is a team of the chemists and engineers with focus to produce high-performance nanoparticles and microparticles by using microfluidic and flow chemistry. So we focus on biomedicals and pharmaceutical industries. We supply standard products such as particle and emulsion stabilizers. We also advise customers on microfluidic setup and processes. And if required, we also undertake proof of principle projects, for example, like feasibility tests for our customer before making a decision to buy the product. With the microfluidic technologies is a technology which enables formation of high monodispersed droplet in range of the micrometer to hundreds micrometer. So it's including a complex structure, for example, emulsions, double multiple emulsion, encapsulate gas bubble, or genus particles, or hybrid materials. So in this, with microfluidic technologies, droplets can be used as a microreactor to create complex formulation, such as the sample can be confined or dilute, mixed, split, or analyzed. So the application of the microfluidic in industries is variable. For example, the microfluidic can be applied in pharmaceutical industries like drug encapsulation and drug deliveries. It can be applied in nutraceuticals industry or cosmetic industry or food flavors and fragrance and research academias. And it also can be applied in biotechnologies and agriculture or other industries as well. So with the arm of Dolomite is provide total solutions for microfluidic. We can provide a full system of microfluidic with the flexible off-the-shelf solution. We also can provide microfluidic components with individual modular accessories like chips, connector, sensor, pumps, temperature controllers, and chemicals. We also can be bespoke like custom solution, like designs to the requirement with, for example, like chip, pump, connector, sensor, or the others microfluidic device. Here showing some example of our customer in the world. So we provide our product to the very famous university or institute, research institute like MIT, Harvard University, or the big companies like Google or NASA, or the pharmaceutical company like Shire, and also the petroleum company like Schlumberger. So it means we provide very wide range application for the customer. So we have a lot of experience in supporting customer with our product. So the next part, we will go to the basic concept of the microfluidic. So if you have a look at the graph in the left side of presentation, you can see the emulsification can be formed by the different methods. So with the two methods, the first method is by the traditional methods like batch methods. In this method, so two immiscible solutions we're mixing in the batch reactors, and we will apply the energies like stirring or sonication, so to making the emulsions. So for example, in this case, we can make the emulsion of the water in oil. So because of too many factors can affect in the batch methods like temperature, mixing, or energies applied like stirring. So it's caused very poorly dispersed in the particle size distribution. It's different with the batch methods, the microfluidic methods, the emulsification by pinching droplets, not by whisking. So in this case, we pumping the two solutions in continuous phase and droplet phase through the chip junctions channels and to make droplets by pinching. So with advantage of flow chemistry, like the easy to control the temperature, easy to control the flow rate, so the droplet size can be easy to control to make up the very precise particle size distribution. So in which microfluidic is very monodispersed particle size distribution. Here showing some example of the droplet formation by using the exjunctions of the microfluidic chip with pumping by the droplet phase and continuous phase, and we can make up the droplets. Or we can make up the two different reagent input chip, so to make a droplet with two different reagents in one droplet. So every parameter is easy to control with our software. like pressure, flow rates, or temperatures. So what we need for running a microfluidics experiment, we need the three main things. The first thing is a way of moving fluids. So it means we need a pump. The second is a way of adjusting of surface tension of absorbed fluids. So it means we need surface tension to stabilize the droplets at the formation. And the third one is we need a microfluidic device where the application runs. Means we need a glass chip or microfluidic chip to run the application. Here is showing a wiring of the methods to form the droplets. So basically, we can make a droplets by using the T-junction to form slot with larger size and junction size. Or we can make a droplets of emulsions by using the X-junctions to form the droplet with a wide side range relative to junction size. Or we can make a double emulsion by applying two chips. So the first chip will make a small droplets, and the second chip with bigger droplets which contains the other droplet inside. And we can make an encapsulation by placing one or number of the cell particles inside the droplets, or we can make nanoparticles or crystallization by mixing up two streams and subsequent isolation of reactant into the droplets. So the particle generation can be occur inside the droplet, and it's very easy to control the droplet size in the side of the droplets. And we also can make up the very complex particle like xenous particles by incomplete mixing of two streams to forming of particles with heterogeneous surface properties. So by changing a different of the flow ratio or flow condition, we can make a different mode of flow. It's including the drift regime. We can make a mono disperse of droplet formation, or we can make a jetting regimes. So it means we flowing too fast, so to create the laminar flow. Or we can make a child state by adjust ratio or the backflow. So it's unwanted process can be occurs by the pressure imbalance. For controlling droplet size, there's two ways to control the droplet size. The first way is using the different chip junction size. With the bigger, larger chip junction size can make a droplets droplet size, and with the smaller chip junction size can make a smaller droplet size. The other ways is we can control the droplet size by adjusting relative flow rate ratio of the continuous phase and droplet phase. So, for example, if we increasing the flow rate of the continuous phase in here, so we can decrease the droplet size. Or if we increase the droplet phase flow rate, we can increase the droplet size. Or if we increasing both continuous phase and droplet phase, we can increase the droplet production rate. The chip surface coating is also one of the important factor can be affect in the microfluidic. So let's say about if you want to make the oil in water emulsion, so you need to hydrophilic coating on the surface reactor. In the batch methods, for example, the batch reactor or the beaker need to be hydrophilic function. So in this case, so emulsion is the droplets, we cannot contact to the reactor phase, and it prevents any integrate or any integrate of the droplet to make it to make a droplet more stable. So in the microfluidic also is similar. So we need to coating surface of chip by hydrophilic in case of the making oil in water droplets So in this case, droplets, oil droplets will be do not contact with the surface of chip, so it can make the droplet more stable after formation. So by reserve way, if we want to make the water in oils emulsion, it means oil is here is continuous phase or dispersed phase. So we need to hydrophobic coating, which prevent the contacting of the water droplets inside with the surface of the reactor, or fluorophilic coating if you are using the fluorinated solution to make up the water in fluorinated oil. With the particle generation by microparticle and nanoparticle, we have two methods. The first method is droplet forming method to making droplets. So in this case, microparticles will be formed in the micro size by using the droplets. So in case of nanoparticles, you need to use the flow focusing methods. In this method, we pumping two solutions into the chip junction, so to making laminar flow, and because of different dissolubility of the reagent or reactant, so during the mixing parts with the laminar flow, the precipitation of the reagent will occur between the surface of the two streams. So the nanoparticles after formation inside the chip will crashing out by the solvent or continuous phase. So there's a lot of methods to form particles. We can use chemical methods, or we can use rapid mixing as by the mixing in showing the flow focus methods. Or we can make a solvent extraction, or we can make a thermal treatment. We can make UV polymerization, chemical cross-linking, or nano precipitation method. So next we will move to the application of microfluidics. So I would like to talk about the first application with the PLGA microparticles. You know, PLGA is a polylactic glycolic acid. It's a biodegradable polymer, and it is FDA approved. So it allows to control release drug or API, active pharmaceutical ingredient within the body. So in this method, we're using the chip junction to making droplets to make a microparticle. So the continuous phase should be water, and PLGA is polymer, so it should be dispersed in the organic solvent like DCM, dimethyl chloromethyl. So with the concentration range from 0.1 to 20%. So after creating the droplets, so the droplet inside will contain the PLGA and solvent DCM, and the DCM will be extracted into the water phase during the time. So if you see, have a look at these photos, it's showing the droplets shrinkage during the time by solvent extraction or solvent evaporization on glass slide. So by the time, so microparticle on the PLGA after solvent extraction will be formed. So here, this showing some video showing more clearly about the PLGA solvent extraction with the industrial diameter around 80 micrometer. So by the time, so the particle will collapse by solvent because of solvent extraction. And finally, very fine particle with size of the 24 micrometer PLGA can be generated. So the next is some application for the API or the drugs encapsulation. So we can make with the different PLGAs multiple emulsion. So in this case, the multiple emulsion is mean the small droplet contained in the bigger droplets, So in this case, we use the two different chips. The chip 1 is a small chip. We can make the small droplets of water in PLGA and DCM. And the second chip will have the bigger size, so and it can make the bigger droplet which contain the small droplets at a product of the initial chip inside. So it will form the multiple emulsion droplet of water in PLGA and DCM in the aqueous phase. So in this case, it's very useful if we encapsulate. We use this one for encapsulate APIs inside with the hydrophilic. Thus, we cannot disperse in the polymer phase. So we have to disperse in the aqueous phase. So in this case, we disperse API in the first chip as initial time with the liquid water phase. So to encapsulate, to make up the water in oil solution emulsion. And after formation of the multiple emulsion, so the API will be encapsulated inside the PLGAs. So here showing some images of the multiple emulsion. So it showing the very monodisperse of the multiple emulsion can be generated, and very even distribution of the monodisperse of the small droplet or the API inside the PLGA by fluorinate the images you can see in here. So these methods have very high encapsulation efficiency from 50 to 90%, and it's highly reproducible process. So the next method for another application with the direct powder encapsulation. So in this case, if the API or drug cannot be dissolved in water phase or both organic phase, so you have to encapsulate as a powder type. So the setup is very simple, just using only one chip, typically 100 micrometer chip. So you have a look at here. So droplet phase will be including the polymer like PLGA and the powder API and solvent to make a suspension. And you make a droplet with content of the powder API and the polymers PLGAs in the DCM. So after DCM solvent extraction or evaporation, you can make the APIs inside the PLGA's particles, microparticles. So here is some results. So it's showing the high efficiency drug encapsulation with the 60 to 90%, 95%, and high process reproducibility and event distribution of the API within a bit. We can show in the fluorinate the images, and also it's a high particle monodispersity. So you can see very well distribution side, particle side distribution. And it's very easy of control over drug loading and high control over release profiles. We were talking about the microparticles, so now we are moving to the nanoparticle PLGA methods. So as I mentioned in the slide, previous slide, so is this to make a nanoparticle, we need to use the micro hydroflow focusing methods. So in this method, basically polymer particles, polymers is dissolved in the solvent, and we pumping with the water phase in here to make up the laminar flows. So this method forms using the process of the nucleation and growth. So it means because of different dissolubility of the different solvents, so in interface, it's between interface surface of the two streams. So the nanoparticle will be formed by different dissolubilities and the crossing out at the chip. And here showing the simple example for chip setting up, we use a 5-input chip. So the interface will be using the PLGA solution, and the outer phase in here we will flux the anti-solvent solution like water or buffer solution. So here showing the image, we visualize the inside chip junction. So we can make a laminar flow in here, and between of the interface of two streams, the nanoparticles will be formed, as you can see here. And with this method, the particle size is controlled by just adjusting the relative flow rate of the continuous phase and droplet phase. And also, with this method, the API can be encapsulated by brought in both continuous phase, in case of the hydrophilic, which can disperse in the water, and the interface, in case of the hydrophilic API or drug, so we can disperse in the organic phase. So the result showing with the fine input chip we are using, so the particle size were controlled in the region of the 100 to 200 nanometer by just adjusting a different flow rate ratio of the polymer solution and aqueous phase. So the next application is the liposomes nanoparticles, and the other application as well. As we know, liposomes are vascular nano and microparticles which form by lipids bilayers that encapsulates an aqueous volume inside, which can be used to encapsulate the hydrophilic drug or API inside of the aqueous phase in here. And the liposomes are widely employed at drug delivery system. So similar to the nanoparticle method of the PLGAs, so in this case we are using some hydroflow focusing methods. So we pumping of the interface lipids in ethanol and the outer phase water or the buffer solution with the surfactant. So in this case, the size also can be controlled by flow rate ratio and the total flow rate. And API also can be dispersed in by both the continuous phase in case of the hydrophilic and interface in case of the hydrophobic, or can be encapsulated afterward by active loading methods like traditional method. So here showing some simple setup for micro hydroflow focusing methods using our chip with the 5 input chip and micro mixer chip. So here showing the image showing the 5 input chip, so we can make a laminar flow inside by the lipid as interface and water phase is outer phase to make a laminar flow stream inside here, and the nanoparticle is believed to form in the interface of two streams. So in this case, by changing the flow rate ratio, the particle size is controlled in region of the 60 to 250 nanometer with the both of the 5 input chip and micro mixer chip. With the other particles, so we also can make with the alginate, agarose, or soft and harsh polyacrylamide beads, which can be applied in many ways, many applications like drug delivery, drug encapsulation, or pharma, or cosmetic, food industry, agrochemical industry, and screening and R&D. So we will talk about our system from lab to commercial scale. So here, showing the single channels system, which will including the basically 3 pump, pressure pump. So the first one pump for continuous phase, the other pump for interphase, and the third pump for flushing or cleaning before and after your reaction. And the pump will be connected with the microfluidic chip by the tuning and the interface, like we call it edge interface. And the process inside the chip will be visualized by high-speed microscope, high-speed camera microscope. And in the single channel system, the production yield will up to 1 kilogram per month. So it's very useful and useful in use in lab R&Ds or with studies or research academia. To increase the product scale, So simply, the simple way we can increase the production scale by increase the chip channels, the junction channels. So we use a multiple channel to increase, or we can use multiple chip with multiple junction or multiple channel to increase much more the production scale. So with Telos scale-up system, we increase output by 3 distinct ways. First is increase the flow rate through the individual junction, and the second is increase number of junction working in parallel, and the third is increase number of chip working in parallel. So in our Telos chip, we can make a 7 chip junction. We can work in parallel, so we can increase the production up to 7 times. So with it's one chip, and we can integrate or stack of the chip up to 10 chip working together by using our Telos modulars, which show in this slide. So we can integrate or stack together of the multiple Telos clamp up to 10 chip working together. So we can increase up to 10 times compared to single channel, a single chip. So here showing some example for a 5 chip Telos system to making PLGA Droplet which we're using in the industry. So please see in this video. Please see in this video showing the different chip junction working together in here. And here is a pump and extend device the chamber to increase the reagent content. And here is the 5 input chip working together in parallel by some Telos modulars. And the other pump is a custom part. We can also increase the volume of the reagent can be used in case. So if you have a look in the production, you can see it can be run at 12.5 ml per min. So it means it can make a 1 ton per month at 100 ml per min. Totally. So our system Telos application available in single emulsion, double emulsion, liposome synthesis, polymer nanoparticles, polymer microparticles, and hydrogel synthesis. Summarize. Okay, so what we do need, what do we need for running microfluidic experiment? So remember, we need 3 things. The first is a way of moving a fluid, a pressure pump. The second is a way of adjusting of surface tension of the fluids. You need the surfactant to stabilize those droplets or particles. And the third one is a microfluidic device where application run. So you need a glass chip. So Dolomite can target many key applications in the areas of the PLGA and liposome or other particles such as polymeric microparticle or nanoparticle synthesis, which can be applied in the wiring, for example, API, encapsulation, food, cosmetic, catalysts, or patent drops, more and more. And Dolomite product and particle engineering team expertise enable and used to achieve the high performance and reproducibility. And Dolomite process can be scaled to pilot plant production level using multiple modular Telos system. Here showing some example of our customer in Asia. So we sold our system to the university in the China or the pharmaceutical companies in China as well. We have a customer in University of Melbourne from the Australia, or the LG from the Korea, or Nanotech from Thailand, or Sunway University from Malaysia, or National University of Singapore in Singapore, and more. Okay, so I finished the section 1 with the presentation. So if you have any question, just feel free to typing down in the text box. So I will try to answer the question in the Q&A section. So in the next section, it will be a live demos. Sorry, I should stop. Okay. With a live demos with our basic system, as you can see behind me. So with the basic system, with including the 3 pump, pressure pump, with 2 pump are using. First pump will be used in the interface or the droplet phase, and the second pump will be used in the continuous phase in here. So the pump are connecting with the chip in here, and the process, the droplet formation will be visualized by using the high-speed microscope. Okay, so today we will running a demo with the droplet formation oil, water in oil. So it means today I will use. Remember, I will use the hydrophobic chip. Oil is the continuous phase, and droplet phase is water. So, okay, I will share my screen again to see that our software can be controlled, how our software can be controlled with this system, with the 2 pump and microscope to visualize the droplet formation inside the chip. I will share again my screen. Okay, good. So in here is our software. We call Dolomite Flow Control Center software. We can control the parameter of our product. So now it's connecting to 2 pumps, as you can see here, and a microscope. We can see the chip junction inside here. So this is a 3D pore chip with the hydrophobic surface coating. So it means we're using the continuous phase in here is hydrophobic, is organic solvent like oil, and the droplet phase is water in this case. So as you can see in here now, the first pump is oil. So I already applied. The pressure is 2000 millibar here, but I didn't turn on the valve. Actually, we have a valve we set up connecting between pump and microchip. So now the valve is closed. So there's no flow rate pass through the chip as well. And this pump will be the water. So I applied the initial 1000 millibar. So without the pressure pump, the maximum and our system, the maximum the pressure can be applied is 10 pump. So in this case, flow rate or pressure can be controlled by the option in here. So it's pressure controls you can here, but if you want to control by flow rate, you can click here. Similar in the second pump with the water phase, and in here we will visualize the process in the chip. So now I will do is to open the valve first. So we will starting with the oil phase in here. So I will open the oil phase. So now you can see the oil is passing through the continuous phase, and so now the flow rate is around 20 microliter per minute. And I will open next with water phase here. So you can see the droplet is generated through the chip after I opened the water phase, which is around 3 microliter per minute. So the flow rate ratio is, in this case, around 7. So I will change to be stabilized the flow rate in this case. So I will change to flow mode. For example, in this case, I will change to 3 here. And now the flow rate of the oil is also 20, around 20. So you can see the droplet with the sign here. So in the presentation file, as I said, we can control the droplet size by changing flow rate ratio. So now I will increase the flow rate ratio. It means I will increase the continuous phase, the oil phase in here, by increasing the pressure. For example, now I increase the 3000 pressure millibar in here, and we can see. Okay, the first time because the adjustment so it will affect them. So the droplet size you can see in here will be decreased with higher flow rate, the production rate. So now the flow rate is 30 continuous phase and 3. So it means the flow rate ratio is 10. So you can see the smaller droplet can be generated. Or we can increase more, I'm not sure, 4000, let's say. So when a second is will stabilize in a second. So here, yes. So now you can see the smaller droplets can be generated. Yeah, we can pop out in here to make to bigger images you can see. So you can see here. So the droplet will be formed after the pass through the chip junction. So in this case, we're using 3D pulse chip with the 100 micrometer chip junction size. So droplet size will be ranged from 80 to 120 micrometer, depending on your flow rate ratio. Okay, that's our live demo to show you how our system can be worked to generate droplet or microparticle. So if you have, now we are moving to the Q&A section. So if you have any question, please feel free to ask me through the chatting box. So I will try to answer everyone. Oh, how I can stop here? It wasn't working. Okay, maybe it will work here. So it will be showing in here. Any question, please? So by using the chat box function in here, you can see in here. So you can type in the question in here. So I will try to answer if the question is short because we have 15 minutes, 10 to 15 minutes in the Q&A section. Is there any question? Just feel free to ask me and ask our teams.
Ya, kepada Bapak dan Ibu sekalian, silakan kalau ingin bertanya, dan bila ingin bertanya dalam bahasa Indonesia juga boleh, nanti akan kami terjemahkan. There's one question, I think.
Okay, I saw the first question. What is the minimum dimension that Dolomite microfluidic can be fabricated? Okay, so the dimension Dolomite microfluidic chip can be fabricated with the minimum is 5 micrometer. It's a 5 micrometer chip. Okay, so second question is what kind of pump do you use? So we are using the pressure pump. In here, you can see in here, pressure pump with we have the pressure chamber. It means we can apply pressure in the chamber, and we put the solution inside. The solution inside here. through the wire. So by applying pressure, the solution will flush out and we will control flow rates by measure flow rate by flow rate sensor or control flow rate by pressure. So with the pressure pump, we can make a very smooth or pulseless flow, which very important in the droplet generation or microfluidic. Yes, so you can set up the pump to be flow rate driven or pressure driven through PC. Yes, absolutely. So we have two different modes of our P pump. So pressure pump with the basic pump. So we just only control pressure control parameter by the software, our software. The second, the other thing is advanced pump. It means it will have the knob control in each pump, so we can control the pressure or flow rates by both functions, from the pump knob and from the software as well. Okay, next question. How about using 3D printer from Dolomite? Yeah, it is possible 5 micrometer. How about the transparency level? About the 3D printer from Dolomite, we are using the COC's material, so the transparency level is not quite good like glass, but it's just enough for visualize the process inside a chip. And with the 3D printers, the maximum is impossible to make up the 5 micrometer chip by 3D printer. So the maximum is 300 micrometer by using the 3D printer, because of limitation of the 3D printers with the COC materials, polymer materials. Next question. Is there any question more? I don't see. Yeah. Okay. Next question from the Tigers. Okay. How big is the diameter of the fluid channels? And it's made by glass. It's possible if we disperse. If we use a dispersion. Okay, if we use a dispersion or already is emulsion or other fluid emulsion. Yeah, so the diameter of the fluid channels is range from the micrometer to hundreds micrometer. So we can range the chip junction from the 5 to I believe the 190 is the basic standard chip, or we can do a custom job. We can, if you want to make the different size of the chip junction, like bigger than 190 micrometer. So yeah, it's made by glass and quartz. It depending on the application. If you, basically it's made by glass, but in case of the photo reaction like UV degradation process, so we also provide the quartz type. Is it possible if we use this person? Yes, as I mentioned that in our application to make a multiple emulsion, we can make up the emulsion as an interface. I mean the droplet phase. So or the suspension in droplet phase. So it depending on your viscosity. So in this case, viscosity is also important. Oh. Is internet của anh bình thường không? Okay, sorry. So it seems like my internet poor connection. So yeah, so it means you can use with this already dispersed solution or the emulsion to pass through our chip to make a double emulsion or multiple emulsion or powder encapsulation. Yeah, I will show the chip. Sorry, yes, in here. Okay, can you see clearly? Lana can help me. Yes, now you can see. It's our chip in the 8 interface connector and linear connector. So it will connect with the tubing. It's a droplet junction chip with 100 micrometer size. You can see in here. So the channel in here, the channel of the chip junction around the 300 micrometer chip channel is a 300 micrometer, and chip junction is a 100 micrometer. What happened? Okay. Okay. Okay, the Dolomite have integrated hardware, software, monitor, droplet size, content. Yes, actually, yeah, I forgot to mention in the presentation, but we have a software we can exactly controls the flow rate to achieve the droplet size. Or I will show you in the other slide application. Wait a second. Here, you can see in this slide, we have a quality control by prototype the software to a select customer. So the feature of this software, including the analyze size of multiple droplets within a region of interest. So also it can create a live histogram to record the droplet size, and also determine the droplet formation frequency by direct observing droplets or by calculation from the droplet phase, flow rate, and droplet size. And it can be automate controls like stop production if the system is no longer making droplets, or cruise control ability to automatically varies a flow rate to change set of droplet size. I mean, if you want to make up the predetermined the droplet size, you just set up your parameter in here, and the system will automatically adjust the flow rate to obtain the wanted droplet size. So it's ability to work with multiple chips in the system, and it can be integrated with the other hardware if the customer requires. Okay, it's clear to use and done. Okay. Okay, sorry. It's used to make a lipid-based delivery system such as solid lipid nanoparticle with nanometer size. Yes, sure. Yes, actually, in the last slide, I already showing the application with nanolipid nanoparticle lipids. We can call it liposome nanoparticle or lipid nanoparticles. So it's by the flow focus methods. So we can easily to generate the lipid nanoparticle with the nanometer size by our system with using the 5 input chip and the micro mixing chip. It's clear? Okay, so maybe we have more 5 minutes. So yeah, my 5 minutes you can ask me. I will try to answer. So any question? Any question? Feel free to ask me. Mute. Okay, so if there's no more question at this moment, so yeah, thank you very much everyone for attending our workshop today, and thank you August for arranging the workshop to our customers. Thank you very much. And if you remember, if you have more questions, just feel free to contact us or contact to our friend August. So we are happy to answer you all your question.
Thank you, Dr.
Thank you. So bye bye.
Presentation. Terima kasih Ibu-ibu sekalian, Bapak dan Ibu sekalian. Sampai bertemu di webinar berikutnya. Terima kasih.
Thank you very much.